that's okay. So let's have a look at the signal. Here we see two signals. It has a 4-bit ID, and we can switch the ID bits via dip switches. Here one can see those bits, and I switched one, and one can easily see its Manchester code. This is a screenshot from Audacity, and it is just sent in case of an alarm event, so there is no heartbeat signal or such from the sensor. This is why our hacker tool works. But there are also ones available with heartbeat signals, but they are sometimes in the range of 10 minutes or so. So if the burglar can break into a house within 10 minutes, the alarm is completely useless. Well, it was boring. The fun wasn't worth the $40. So let's have a look at some other stuff. There are a lot of infrared transmitters and receivers available everywhere, and this is usually done by applying the data to a carrier frequency. And the common carrier frequencies are 30 to 38 kilohertz or 445 kilohertz, and the sniffing effort depends on the carrier. So here we can see a few receivers. This is this is a receiver that is used for 30 to 38 kilohertz. It does already digitalize the signal, and you get a 0 if the carrier is there, and 1 if the carrier is missing. So this is, you can just read the signal very easy. And this is the same for 445 kilohertz, and here we have an infrared diode from which you get raw analog data. And this is rather hard to handle because you need to amplify this signal by a great deal. And yeah, this is all done in this IC usually. But you have to use such a diode if you don't know the carrier frequency, and you usually don't know it when you see a signal for the first time. You could of course just try a few carriers. Okay, they can be used for asynchronous serial transmissions up to 2004 kilobaud. So one could easily put the RS-232 interface just to over infrared. One can transmit it over infrared, and RS-232 is a no return to zero interface, but that doesn't matter since we have the carrier here, and yeah, and the automatic gain control will handle it. So if you want to see infrared transmissions, look for daylight filters. You can see them; they are black, like here, or dark red. And where can you find these transmissions? Well, in hi-fi remotes, usually the most common application, remote-controlled vehicles. There are flying helicopters available, and there are also interfaces, infrared-based interfaces to cigarette and drink automats, and the infrared transmissions are used in public transfer. So if you see omnibus with those two circles on the side, these are infrared ports, and you can spot these things rather easy with your cell phone cam. So this is a picture taken with my cell phone camera. The infrared gets a bit through the filter, and you'll see the transmissions there. Well, you see that there is infrared light, but you can't record the transmissions because 25 frames per second aren't enough. Okay. Other infrared devices, here from Starbucks, flat, here from the radiator, it counts the heat, and one gets a bill depending on the amount of heat when used. And this is a water meter, and it looks to me that it also has infrared in it, but it could also be 433 or 868 megahertz. So these devices, both of those devices, are also available as wireless versions. The janitor or so can just pull them while going through the house, or yeah. They can also be resetted via wireless transmissions, I should say. But we won't do this, of course. Okay, let's get back to more complex devices. Memory interfaces, they are parallel interfaces, and they usually have 8, 16, or 32 data bits. One also has control lines like read and write, and there are sometimes also lines to extend the access, to add custom wait cycles, and for slower I/O devices, for example. This is how PCMCIA works. And if you want to have a closer look at the PCMCIA stuff, you can have a look at the Afrolus link I added in the pentabaf. So I added at the talk side. But let's get back to the flash memories. And this is where the software for set-top boxes, PDAs, and all this stuff is stored in. One can use software to dump it, so there are no costly hardware needed to do this thing. But they are high speed, so when tapping the bus is rather complicated. But as long as you control the whole thing, you can give the speed. And you can do it with a parallel port. This is what I did here with a flash memory from a handheld mobile, whatever, it's kind of BlackBerry style. And you just read the datasheet and implement the bus in software. And then you can read it out. Of course, you have to do some soldering. And you have to get some practice with this. And also a hot air station is rather useful, but they are already available for $60, so you can do this at home. Okay, so what do we use to interface hardware? Well, for the analog part, to get a first impression of the signal, oscilloscope is very useful, but it is also expensive. So there are a few low-cost substitutions. For example, for this 333 megahertz receiver, we used a sound card, and to get a 48 kilohertz sampling rate, or with the high definition sound cards, you get a 96 kilohertz sampling rate. So this is enough to get 24 kilohertz signals clearly, or 97 divided by 2. The ADC of a microcontroller is also a useful thing. Example, this A4R 8-bit microcontrollers, they can do 666 kilohertz sampling rate, and the ADC clock is half the clock of the system, and it needs 12 cycles for one measurement. So this is why there are 666 kilohertz sampling rate. It is very nice because you have 10 bit, and you also have 200 times gain. This gives you a precision of a few microvolts, and you can just put the infrared diode to this ADC and add some trigger point for detecting the signal, and at another value, and you say 0 is below this value and the 1 is above this value, and you have your digital signal. For example, one can just hook such an infrared diode, I have one with me, to such an A4R microcontroller and sniff the TV begun thing, and just build his own without buying the components. Back to the digital part. There are logic analyzers, but they are very expensive. And you can put something together in most cases. And then another advantage of putting something together yourself is that every problem is different, and so you need a different solution. And this makes custom hacks necessary. Okay, the parallel port is very slow. You can do only a few kilohertz sampling. While a scheduler is running, there are some hacks to turn interrupts off and such stuff, but I think this is rather messy. So I am using external logic, but you can do 2 megabytes per second with ECP-enabled parallel port, and you also get DMA there, so this is a very nice thing. It is also faster than full-speed USB. You can use a microcontroller to do the real-time sampling, of course, and a CPLD or FPGA if necessary. The RVR 8 bits are slow but easy to program, and they are great for hard real-time because you know the exact time in cycles every comment takes, and there is no cache and no complex pipeline. So you can just say this branch will take 2 hours if taken, 2 cycles if taken, and 3 cycles if not taken, or whatever, and just have a look into the datasheet. This is another thing with the ARM microcontroller. They are very fast. They are 32-bit. You have lots of SRAM up to 64 kilobyte, and they are fast, and one can not do hard real-time that easy because there are pipelines and caches, and yeah. You have to use some sort of hardware support then. For example, timer-based sampling or such stuff. Also, when grabbing data and transmitting it to the PC, use a ring buffer and use an overrun indicator. Or you'll analyze the data just to find out, damn, there's one sample missing, it's all messed up, and you wasted your week analyzing that. Data can be transferred via RS-232 if it is below or equal to about 9 KB per second, and full-speed USB gives you about 1 megabyte per second, and high-speed USB gives you below 60 megabytes per second. This can't be said very easily. The exact speed you have depends on the controller and such stuff. You have to test it. One can also use the hard disks interfaces to get data hellish fast into the PC. So parallel ATA gives you 130 megabytes per second. So you can just emulate a hard disk using a bit of gluing logic like FPGA, a small one. Maybe it is even possible with it should be possible with a CPLD. And you can also use serial ATA, but this is low voltage differential signal, and this the signaling is a bit messier here because you get several gigabits, and if you have a 90, the routing the lines is very complicated then. So there's no interference. Ethernet doesn't make any sense because it is very complicated, and with 100 megabit you only get 12 megabytes per second in the best case, and you have protocol overhead and all that stuff. Okay. Questions you should ask yourself first before doing anything. How much data do I want to log, and how many signals? No fast interface is necessary if you can put the data completely into your buffer space. This is true for the ink cartridges. I just used an HVR to do this thing, and I just used the internal SRAM, and I added a button to give me the data via serial interface. And the next thing is, what's the maximum speed of the signal, and how do I get an appropriate sample rate to digitalize this signal, or to grab this signal? And depending on that question is the question, what interface do I use to transfer the data to the PC? Of course, this has to be fast enough. We'll see some sort of solution in the next slide. And to answer this question, the how much data question also. And okay, the next question is, how do I store the data in the buffer? One can often compress the data a bit. And how do I send the data to the PC? The question is, do you have enough processing power to store it in this particular format? And do you have enough throughput to the PC to send it in this particular format? For example, I2C, we have 2 lines, so we can just send a byte per sample. This makes 6 unneeded and unused bits. So one can put 4 samples into 1 byte.